So let's start with some questions before the lecture. So the first question is regarding the extended Kalman filter and the way how the transition matrix is computed. So if you look at this slide here, what we are doing here is trying to propagate the covariance matrix of the quaternion. So it is the transition matrix that is referred to the quaternion itself, and what is done afterwards. So what we have here. So phi is divided in three submetrics. So you have basically theta, psi, and the identity matrix. So what happened here is that, so in the next slide, we use the integration of the different submetrics in order to compute the final phi that you need to include in the computation of the covariance matrix. So here is not indeed the transition matrix that you have seen for the orbit determination. So here phi is the transition matrix that enables to propagate the error. So basically is indeed minus omega t cross. So basically we need to propagate the error. That's the reason why the theta here at the first instant is starting from the identity matrix, psi is starting from 0. But as we said during the exercise, that probably we are going to redo briefly next week, you can indeed see that what we are going to do is that every single time the transition matrix is updated. So basically we have that the second at the instant, for example, tk, that will be the transition matrix that is propagated from the previous instant. So we are starting from this condition, but afterwards we are going to use the information that was accumulated in the previous step to determine these submetrics. So basically the idea here is that the transition matrix is divided into two different matrices. And these simplify the computation, because in order to compute a 6x6 transition matrix, you see that you only need to propagate basically the two submetrics theta and psi. The propagation of the error due to the quaternion is implicitly in Q. But as I said during the lecture, the propagation of Q here is roughly explained in the sense that basically what we have is that if you want to propagate Q, you should indeed use the matrix gamma. So you need to do the integral of phi times the matrix G. That is the matrix that connects the delta Q to delta B. So this part of the process noise, as I said, is only for your knowledge. What I would suggest, and this was one of the questions that I received yesterday, is usually to try to tune your filter by possible different values of Q. So for example, that could be a good exercise, and not for realistic simulation, of course, but only for academic purposes, to try to change Q, for example, with a Monte Carlo. So starting from a larger value to the value that is close to R, and see what are the values of Q that provide the best fit of your Kalman filter. That could be a good approach because, I mean, for you will enable, I mean, you will be able to determine if the filter will converge to a good solution or not, because are simulations. But on the other hand, the basically what I mean, you have also a simplified system because you don't need to integrate the cube in your exercise, basically. So let me know if I mean, so that the question of the transition metrics was regarding the difference between theta and psi, right? So this question.
Cioè, professore, io non ho capito, quindi la prima parte in cui dice che dobbiamo integrare φ partendo dall'identità non va bene, cioè non lo dobbiamo fare. Dobbiamo calcolarla in quest'altro modo. Questa era la domanda. Cioè non ho capito perché c'è scritto che dobbiamo partire come nel problema di determinazione orbitale, mentre invece poi seguiamo quest'altro approccio.
But, so, quindi
cioè mi sono confusa.
A questa slide qui.
A quella di prima in cui c'è scritto di integrare.
Okay. So here you mean this? Okay, this phi here. Okay, so
sì.
I mean, it's exactly the same approach. I mean, it's not, there is not inconsistency between this approach that you have here and this one. So none of the two is wrong. So what it is meant here is that what you can do, since if you can see psi is indeed the off-diagonal matrix. So if you are starting from phi, that is identity, means that you are starting from theta, identity, and I is also identity. So this is 0. So you are starting exactly to the same condition. What it is meant here is that you can separately integrate a submatrix 3 by 3 and another submatrix 3 by 3. So there is no inconsistency between the two. So probably, since now we need to start from we need to start the lecture. We are going to do an exercise next week. So what I'm going to propose, indeed, is to do an exercise, a simplified exercise with Quest algorithm, triad algorithm, and the Kalman filter, if you are interested in doing the Kalman filter. And we can re-see the software that we have shown last week, or actually on Monday, to better explain how the transition matrix is propagated. Because, I mean, as I said during, I mean, on Thursday, here there is not an explicit form of theta and psi. So I can understand that it's not really clear from the slide. So if we are, let me give you a few examples with that software that probably will answer your questions and probably solve your main concern. But there is no inconsistency between the two. So probably. Sì, prego.
Una domanda velocissima le volevo fare, se aveva detto che stava per cominciare la lezione a tale riguardo Q, mi aggancio anche a questa domanda in cui spiegava il ruolo di Q, ma Q essenzialmente, quindi in pratica quello che facciamo è dargli una forma simile ad R e aggiornarla durante il processo di integrazione, cioè gli diamo una forma, per esempio, che ne so, diagonale con un certo peso che poi vediamo se a fine integrazione dà un risultato soddisfacente, una cosa di questo tipo.
Okay, so let me translate this question. So the matrix Q related to the process noise is indeed, I mean, how it is written and is proposed in the slide, I mean, it is solved only by using the propagation with gamma, okay? What I'm suggesting is indeed to do a simplified approach. So what you can do indeed for academic purposes, try to scale the matrix in a way that you can see the response of your filter. So the suggestion that you gave, indeed, trying to use a diagonal matrix that accounts, for example, for the gyroscope initial errors, could be a good solution. So let's try to do that and see, for example, if you have a diagonal matrix similar to what you have for R that accounts for the errors of the star triggers, and try to see what you get. So that's my suggestion, but it is only for academic purposes, of course, and also to better understand how the tuning of a filter is done. In reality, what you need to do is indeed try to build the matrix Q in using this process noise. So I think that, I mean, there are probably many questions that we need to address regarding the Kalman filter. So that's the reason why. So let me see. So let me pause the recording. Going back to the sun sensors. So I also got the other two questions yesterday by email. So I tried to explain the differences about the tuning, but of course, as I said, probably looking back to the exercise will be probably easier. So next week we will do that by solving a given exercise. The other question was regarding the Earth sensor. So before concluding the sun sensor here, let me go back to the Earth horizon sensors. So the last part that we have seen yesterday is a different approach to confirm one of the main weakness and limitation of the sensor. As we said, if you have only one Earth horizon sensors, what happens here is that you have only two crossing points at the limb of the Earth disk. So what you have here is indeed that you have only two measurements that you can use to determine two angles of your spacecraft attitude. The two angles are roll and pitch angles. So the roll angle is determined by looking at the phase difference of the signal that is measured by the detector. And you have a vertical axis that give you the information about the symmetry of the signal with respect to a vertical reference. And so you have a pitch axis. So the main problem here is that the roll axis, so the roll angle, is directly dependent from the E0, that is the signal that you received at a certain altitude. As I said, the signal changes because the intensity is that you received from your detector is changing, is the altitude of the spacecraft is changing. If you are going higher, the E0 tends to be lower because you are receiving less signal. So the main problem that we've seen from here is that you have three variables, phi, theta, and E0, but you have only two measurements. So that's the reason why yesterday we introduced the dual scanning sensor that has the advantage of two independent Earth horizon sensors, but has also the advantage to be only one single instrument. So that means that you have only one sensor unit that give you the possibility to scan two independent region of the Earth. That's the reason why yesterday we briefly introduced an independent method to determine the Earth. So basically your roll and pitch axis by using a sensor. So the questions was regarding the vector v1 and v2. So as you can see here, we propose an independent method that is only well suited for Earth sensors. So we're not assuming to know other measurements. The only measurements that we get are the one for an Earth sensors that gives 4 crossing points. So here are represented only 2. But if you have a dual scan, as we have seen here, you have other 2 crossing points. So you are crossing the horizon plane of the Earth. And these 2 independent crossing points give you the possibility to determine the position of the spacecraft relative to the Earth's surface. So first of all, we need to determine a reference frame. And the reference frame, in this case, it will not be the inertial reference frame. What will be the reference frame with the z-axis that is parallel to the radial direction of the spacecraft. And as I said, the y-axis close to the for example, the pitch axis of the spacecraft orbit, and x will be close also to the along track axis, so the roll axis. The vector that we have shown here are v because those vector here are the vector represented in the reference frame R. So these xr, yr, and zr. So the only, so what you have here is the expression of this parameter with respect to 2 angles, rho and beta. Rho is indeed the relative angle between, so as the spacecraft is seeing the crossing point of the horizon. So is this angle here for V1 and this angle here for V2. You can easily compute rho that is dependent from the is dependent to the altitude of the spacecraft. So what you can see here is that the crossing point, this triangle here, so this is the center of the Earth. This is the crossing point of the Earth scanner with the Earth horizon. And this is the altitude of the spacecraft. This triangle here has 90 degrees in this triangle. So you can determine that, probably let me write here, that R, E, so the radius of the Earth plus the altitude of the spacecraft times the sine of rho is equal to RE plus HEQ. So HEQ, as I said yesterday, is an equivalent height because basically the crossing point of the Earth sensor will not intersect exactly the Earth's surface, but it will be an altitude of about, for example, close to 40 kilometers. So it means that what you are measuring is the Earth horizon in the infrared emission. And as I said, that is dependent from the absorption of CO2. And this equivalent height is almost equal to the 40 kilometers. So if you invert this one, you see that rho is only dependent from the altitude. The problem here is that beta, you don't have any information regarding beta. Okay, so when you're trying to, so basically the only element that you can use from V1 is indeed the rho, is indeed the Z component, because it's only dependent from the rho parameter, so from the altitude of the spacecraft. This means that when you're trying to compute this vector in the reference frame of the sensor, the component will be function of delta, that is your phase measurement from the detector, and eta, that is the semi-angle of the cone, of the conical path of the sensor. So those parameters are known. So you basically get S that represents your W. As I said, if you consider that you have that your sensor reference frame is consonant to the optical bench reference frame. So you can see that with only one observation, you have only one equation. Why we have only one equation? Because if you try to translate, so if you try to rotate S from the reference frame of the sensor to the R, to the reference frame R, that is this one, you have to use two rotation metrics, theta and phi, that depends on the pitch angle and the phi angle. So here we are assuming that in order to translate this vector S from the reference frame of the sensor to the reference frame from of the orbital reference frame, for example, you have to use these two angles. You can see that if you use the third component of this vector, you have this sum of sine and cosine that depends on eta, that is known, delta, that is measured, and theta and phi that are your unknowns. So if you equalize this function here to the expression of V1 that is only dependent of rho, it means that if you have only two crossing points, you're only able to determine phi and theta if you have information about the altitude of the spacecraft. That's the reason why the minimum number of parameters is 3, because if you have V1, V2, and V3, you can use only the Z component of these three vectors give you information. And so what happened here is that by doing the, equalizing these third component that you have from these rotation metrics of your measurements to the third component of the known vector of V1, V2, and V3, that you can indeed determine phi, theta, and also rho, that is a function of the altitude. If you have only two, of course, you need to know rho. That's the reason why a dual scan Earth sensor gives you more redundant information, because you have 4 vectors. But as I said, it is important, especially when one of the crossing point is occulted or there is interference from the light of the moon or the sun. Hopefully, these explain a little bit better what we have said yesterday. But let me know if you have any questions before I go ahead with the sound sensors.
Scusi, professore.
Prego.
Perché non si possono guagliare anche cioè, perché non si possono utilizzare anche le altre componenti, siccome abbiamo più vettori?
Okay,
Grazie.
yes. So the question is why we are not able to use the other components. So the problem here is that the other two components of the vector of the crossing point in the reference frame R not only depends on rho, and so on the altitude, but on beta. And you don't have any information about beta. So basically, those two components here not only give you information, but also add an additional parameter, beta, that is different for all vectors. So it will be beta 1 and beta 1. And for V2, you will have beta 2 and beta 2. So increasing the number of vectors, so you're also increasing the number of parameters. So that's the reason why the only information is coming from this one, because basically all the vectors, the third component will be equal because only depends on the altitude of the spacecraft. It is clear now. So beta represents an additional unknown that you don't have any information.
Quindi scusi professore, cioè se noi uguagliassimo, diciamo, vengono 6 equazioni, visto che abbiamo 2 vettori,
sì,
e non riusciremmo a ottenere comunque le informazioni su questi 5 parametri che non conosciamo, perché come ci aveva detto ieri, non tutte le equazioni ci danno informazioni.
Esatto. So in principle you have, so if you have, for example, V1 and V2, you have 6 equations. But as I said yesterday, and so you would have 1, 2, 3, 4, and 5 parameters, because you would have phi, theta, rho, and beta 1 and beta 2. The problem is that only 4 of those equations are independent, so you're not able to solve for beta anyway. So you need a third vector anyway, and the third vector give you. So that's the reason why the best way to do that is to include additional vectors and to only use the third component, because at the end you will have 3 unknowns and 3 equations. Because the problem is that the vectors give you 6 equations. That's true. But as I said, if you do the matrix in a matricial form, you will find out that basically you have a deficiency in your rank and you're not able to solve the system. Ok?
Scusi, una domanda.
Sì.
Abbiamo detto che abbiamo definito 2 sistemi di riferimento, quello denotato con R, l'Earth Reference Frame, ma se ho capito bene, praticamente questo sistema di riferimento XR, YR, ZR sarebbe definito come praticamente, diciamo, il piano XR, YR, il piano tangente al punto sotto satellite, se ho capito bene, giusto? Oppure non è così ed è diciamo, molto vicino al riferimento dello spacecraft.
No, giusto. Okay, so the question is if, so since from the figure, okay, so the question is, I'm trying to, probably I got your point. So since from the reference frame here, you have that basically it seems that this reference frame is centered to the, yes, the tangent plane, so the horizon plane of your Earth disk. One would wonder why V1 is measured as it is shown here. So basically, what it is done here, and is not explicitly written, we are trying to compute the versor, so the unit vector of these point, basically.
Io ho chiesto, la mia domanda, forse mi sono spiegato male, aveva un carattere diverso, non avevo capito perché parlasse, se ho sentito bene, di orbital reference frame quando questo riguardo all'Earth reference frame. Io ho capito che è stato definito in questa maniera, però se ho sentito bene è stato detto che è molto vicino al body
ma
frame.
stavo finendo, infatti, no, ma stavo finendo.
Scusi,
Avevo capito la domanda.
Scusi.
So the reference frame that is written in the figure is indeed that the reference frame is centered in the horizon plane. But as I said previously, that you can assume that this reference frame is very close to the orbital reference frame. What is really important here is indeed to report all the reference frame to the same point. So if you basically put this reference frame centered to the spacecraft, you can see this reference frame R as very close to the reference frame, to the orbital reference frame, especially if you have that the spacecraft is moving along a circular orbit. If you indeed put these, you can see that the orbital reference frame has the z component is indeed toward nadir. So you can see an analogy to this one because the minus zeta r is indeed radial and outside. So that's the reason why, if you look at the book, this reference frame is called reference frame. But if you translate, and since we are looking at the orientation of vectors, that's the main point here, you can easily see that if you put this reference frame in this point here, it is very close to the orbital reference frame of the spacecraft. So if you report here XR and YR basically constant to YS, you can see that V1 is exactly defined as it is written here. The problem you have is that when you deal with equations that give you the position, the center of the reference frame is important. Here we are dealing with orientation. So that's the reason why when you see this formulation, you have always to think that all the reference frame are centered to the same point. And in order to do the computation in a correct way, the point that you should use indeed is centered to the spacecraft. Okay, so that's the reason why this reference frame that basically is given by the horizon plane of the spacecraft can be seen as very close to the orbital reference frame of the spacecraft. I mean, this explanation is only to give you a more physical behavior. So because basically, if you are able to connect S with the expression of V, of course, you have a better understanding why, in order to go from S to V, you have to multiply the equations. So you have to multiply S by the rotation matrix of theta and phi, because I mean, if that was not close to the orbital reference frame, of course, those rotation metrics would be different. So that's the reason why I'm trying to do an analogy to that. And so you can see that theta and phi are exactly the pitch and roll line angle. That was your question, or?
Sì, grazie. Quindi praticamente a meno di traslazioni, sostanzialmente quello che facciamo è che a meno di una traslazione il nostro ERF altro non è che per la nostra approssimazione lo spacecraft frame che si distingue per a meno di una di rotazioni dal sensor frame, se ho capito bene.
Esatto. Yes, so the question is that basically there is a translation from this reference frame to this one that is not really reported in the figure. That's maybe the main problem was that, no? Che non c'è nella figura questa traslazione. Però, diciamo, poi, when you have the definition of the vector, this is clearer, because of course, if the row angle is defined, I mean, if this versor is defined as it is here, it is clear that that reference frame is centered to the spacecraft reference frame. So the center is the same. What it is different. It is different is indeed the orientation between the two reference frames. But as we are going to see in the next hour, we are going to approach to the problem of control theory by having a better understanding on how to visualize basically the problem, because I see that many of you, and that is normal, because I think all of us when approached to the quaternion had the problem to figure out what kind of attitude you are gaining if you have a certain quaternion. So for control theory, what we're going to see today is we are going to use an approach similar to what we've seen for the Earth sensor. So what we are going to do is we are going to assume that our goal is to have that the body frame will be close to the orbital reference frame. And in that particular way, you are able to basically approximate that variation in the x and y direction. So if you have a rotation of the spacecraft in the x and y axis, corresponds to indeed variation in the orbital reference frame of the pitch and roll angle. So I'm pretty sure that what we are going to see later will clarify a lot of the things that we already seen in this first part of the course. But before going to that particular problem, and so basically go to the next step of this module, the control theory, we need to conclude the sensor part. So yesterday we briefly introduced some sensors that, as we have said, are very simple instrument, and but although are simple, have a lot of advantages. The first advantage is that you can use sun sensors for many different missions because you are able to see the sun for different parts of the solar system. And so you are able to get information of the altitude for a multiple type of missions. And so that's really a great advantage. The other advantage is that you're able to have also better accuracy compared to the Earth sensors. As we can see from a previous example, I don't know if I reported here, but for example, this Earth horizon sensor has accuracy of about 0.02, 0.5 degrees in the altitude knowledge of the roll and pitch axis. And some sensors can approach accuracies of about 0.015, so lower than the lower bound of the Earth sensors. So these kind of instruments are very important. Of course, are not at the same level of star trackers that we have seen can provide accuracy of arc seconds or even lower than that, but represents a very important standard because, of course, these instruments are usually not really expensive and do not require very large power demand. The reason why are simple instrument is because, for example, we have seen that the simple design of a sun sensor is indeed the configuration of a photocell. So you use a photocell to determine the current that is coming from the irradiance of the sun. So you get these flux from the sun and you convert these flux in an intensity of your current. This current, of course, depends on the incident angle with respect to the normal of the photocell. The main problem is that if you have only one photocell, you will have a strong ambiguity because minus alpha and alpha will give you exactly the same signal. We also have seen with a simple model that at the age of the solar cell, so for example, let's say this angle here, so basically this angle gamma, represent the dead zone in which basically the sensor is not able to provide any information. That's the reason why this dashed line provides you this kind of sharp edge. So basically, you are not able to have information of the sun inclination at angle alpha that are so basically, let's write here. So it means that since alpha is the angle with the norm respect to the normal, you have to be careful that is alpha is indeed so you have 90 degrees minus gamma should be less than this value here. Okay, So this is an important constraint, because otherwise you are not able to get any important signal. To avoid problem given by the ambiguity of the position of the sun with respect to the normal of this sensor, we have seen that you can place two independent sun sensors at different angles. So if you assume that your n here is the norm of the optical plane of the sensor, so this is the sun sensor head, you have a norm, and you put two sun sensors with an inclination plus alpha 0 and minus alpha 0. This configuration enables to get a signal that is basically a result of the difference between the currents coming from the first from the second sensor minus the current coming from the first sensor. And you can see that the resulting curve is indeed a red one. So in the angles between delta alpha and minus delta alpha, you have a sort of very, I mean, is an approximate linear trend of the current response to the inclination of the sun. But you can see here that when you are at angles larger than alpha and delta alpha and lower than minus delta alpha, you have indeed larger errors. So you have ambiguities. You're not able to determine the inclination of the spacecraft, the inclination of the sun with respect to the sun sensor head normal without ambiguity. So the only region that you can use is this linear trend here. And we also have seen, and this is easy to be demonstrated, because you have the delta I is equal to I2 minus I1. And so you have that you're assuming that the maximum current I0 is the same, so you define this parameter K. You have that the first so the second sensor has an input current that is proportional to the alpha 0 minus alpha, as you can see here. The other sensor has a signal that is proportional to alpha 0 plus alpha. By using the properties of cosines, you can easily see that this delta I depends on 2k sine alpha, sine alpha 0, sine alpha. So for small alpha, these can be approximate to the linear trend, okay? You have to be careful indeed that this relationship is only true when the when you are in this domain, so between angle delta alpha and minus delta alpha. To determine delta alpha, we have seen this triangle here. So this is the norm of the sensor S2. And you do basically, you consider an angle with respect to the plane of the sensor here, a generic angle beta. And the intersection of these line with the normal of the sun sensor head give you an angle delta alpha. So delta alpha, of course, is a function of beta. So if you write the sum of the angles, you see that delta alpha plus alpha 0 plus beta plus 90 degrees is equal to 180 degrees. But the angle that I chose here is beta, is a generic angle. We know that at angle gamma, so lower than gamma, you are not able to get any signal from the sensor. So if you substitute beta equal to gamma, you get that your delta alpha is a function of your alpha 0, so the inclination of the sensor with respect to the sun sensor head, and also the angle gamma, that is your dead zone. Larger is your dead zone, lower is your delta alpha. The other conclusion is that larger is the inclination of the sensors, and the larger is and the lower is delta alpha. So basically, if you put the sensors in parallel to the sensor head, of course you're not able to get much information. So that's the reason why the design of the sensor is very important, the definition of the inclination alpha 0 and also gamma, the dead zone. To conclude this part, we can see indeed that these sensors are still not enough, because although these configuration give you the inclination of the angle alpha with respect to a normal vector of the sun sensor head, you only have an information, you don't have a complete information of the sun position. So what you can do, you can use an additional sun sensor with double sensor, the successor photocell, in order to determine the inclination of the sun with respect to a specific plane. So not only have alpha, but also another angle that give you all the information about the direction of the sun with respect to the optical bench frame. A configuration. Yes, prego.
Scusi, una domanda riguardo alfa 0. Mi chiedevo, noi lo vogliamo il più piccolo possibile per avere l'intervallo 2 delta alfa più grande possibile, no?
Esatto.
E quindi mi chiedevo, dato che non lo si prende uguale a 0, altrimenti i sensori coinciderebbero, intorno a quale valore si prendono solitamente?
So the question is, no, this is a correct question regarding alpha 0. So the alpha 0 is indeed, so as we have shown here, we want to have a lower alpha 0 in order to have basically a larger delta alpha. The other problem that I didn't explicitly said previously was indeed that also alpha 0 give you the coefficient C. So you have to find a trade-off between a smaller alpha 0 and a larger alpha 0 that give you a maximum signal of delta I. So if you choose a lower alpha 0, you're going to have a small delta E, a small current. So you have to find a trade-off. Usually, I mean, as it is written in the figure and it is drawn in the figure, you can see that basically an angle could be close to 45, especially for the reason that I just said. So you want to maximize C, but you also try to maximize delta alpha and so minimize alpha 0. So it is a trade-off between the two. But I mean, an angle is not really, there are many different designs of such sensors. So it is tough to explicitly find an angle. A compromise could be indeed between 30 and 50 degrees. So 45 could be a good solution. Okay, so let's have a break here. We're going to conclude with the final configuration of some sensors, and also give you an example of the digital sun sensors. That is basically what is used today. And we're going to start with the control theory just after the break. Okay, so one question is regarding the definition of gamma. So here in this figure, I was trying to explain something that is expressed in the next figure here. So basically, in this figure is assumed that gamma is 0. That's the reason why the lower bound and upper bound of the current that you have from your sensor is half pi. If you consider a dead zone that is called gamma, that should be indeed pi half pi minus gamma and minus pi alpha pi minus gamma as well. So the dashed line that is here is an additional error due to electronics, as it was said correctly. So basically, when you are trying to approach larger alpha angles, this relationship that we have assumed is not totally correct. So it is, of course, a theoretical model of the signal. It is true for larger, for small alpha. Tends to be, I mean, to not be close to the solid line for larger alpha, because as it was correctly said, you have also other electronic error sources that give you unpredicted response of the photocell. So basically you have the dashed line is not exactly equal to the solid line.
Okay, grazie.
Okay, a question regarding the earth sensor is the H equivalent. So since we have a couple of minutes before the next part of the lecture, let me explain a little bit better what it is. So it is an information related to this plot here. What I mean here is that since the detector is going to measure the thermal radiation emitted from the surface, if you don't have any atmosphere, what you're going to measure is indeed the signal given by the surface. So in that case, H equivalent will be equal to 0. But since, as we said, we are going to use the light, so the thermal emission at those wavelengths, we know that the atmosphere is absorbing a part of the thermal irradiation. And so we have that the disk that we are looking at is given by the, after the filtering of the CO2. So that H equivalent basically comes from here. The H equivalent is the altitude at which the CO2 is very close to 40 kilometers, absorb that quantity of thermal irradiation. So since we are looking at that wavelength, those 40 kilometers corresponds to basically a sort of altitude that at which your signal is referred to. So it is indeed an input that you know, because you will know that you are looking at that wavelength. But on the other hand, you also know that basically that value could be affected by some errors. And so that's the reason why these HEQ can indeed also provide some errors in your measurements, because if you assume that your HEQ is indeed exactly 40 kilometers and it is 39, that would affect your error. But in the final accuracy that I said, so these 0.02 and 0.5 degrees in the attitude determination of the spacecraft, all those error sources are accounted for. So you know that the inaccuracy of where the thermal irradiation is generated is indeed important. So represents indeed an input, but it could also be affected by error, because I mean, it is really related by the CO2 amount of CO2 in the atmosphere. So, for example, what it means that the disk that you have will not be uniform because, for example, you have different amount of CO2 in the atmosphere, and so that would also give you a different H equivalent, but also could also provide some errors in the reading of your crossing point. So instead of reading the crossing point here, you're going to read here, because you have some errors in the response of, so in the detection of the irradiance of the Earth.
Quindi noi in un eventuale esercizio possiamo sempre considerarlo come 40 km oppure quello è un valore iniziale e poi con le iterazioni lo correggiamo?
Sì, ma diciamo voi siete sempre preoccupati a questi esercizi. So the problem is regarding the exercise. So if there is a question regarding the Earth sensor, of course, we're going to specify the assumptions. So here we are talking about a realistic problem. So you have to take into account that in reality, there are those possible error sources. If you are going to do an exercise, we are going to tell you, let's assume that we know exactly what is the equivalent altitude. But you don't have to be concerned by the exercise. I mean, the main problem here is to know how those sensor works in reality, because I mean, that's the main problem. For the exercise, of course, we're going to give you a simplified example. We don't pretend that you know which is the uncertainty of H equivalent. It's outside the scope of this course. Okay, so let's go and conclude the sun sensors. As we said, we have found these dual sensor configuration in order to determine alpha, so the inclination of the sunlight with respect to the normal of the sun sensor head. But also, we know that we need an additional angle to determine, for example, our W associated to the sun, because we know that we need at least 2 angles. So we need an independent sensor head with, for example, the 2 sensors located orthogonally to this one. If you do that, you have what you need to determine the W from the sun instantaneously. Okay? But in reality, and that's the main problem, a configuration like that is not optimal, because of course you're going to include many electronics, many sensors. A possible configuration in the analogic analogic design is using the sun detectors placed on a plane. So we need 4 detectors with the YS and the zeta S, the plane of the sensor. So you can see the sensor reference frame. And you can detect from these 4 sun detectors 2 independent current input. The first current input will process the current in the y-axis. So basically, it will be the same case if you place these sensors along the y-s axis. So basically, if you place these 2 solar cells along the y-axis, it will correspond to place these 2 sun sensors in this plane, in this axis here. By placing these 4 cells in this way, you can have an input in the y-axis and also an input in the z-axis that give you this response here and this independent response. So you have 2 measurements of the sun rays. So you have an angle with respect to the x-s axis. So this one, for example, can be seen as the case in which you have your sun solar cells in this way. So this is XS. and this is the second set with XS. So this is an equivalent configuration of the previous sensors that we need to do to have this input. Okay. So in principle, you had to put, for example, 2 sensors in the XY plane and another 2 sensors in the XZ direction. This configuration gives you exactly the same response that you have for this one, but placing the 4 sun cells in the same unit, and will provide a better knowledge of your of the sun sensor, of the sun position, but also will provide a much more compact shape, compact design of the instrument itself. So basically this represents a much more compact design of the instrument, and will provide an analogical signal that is indeed close to a linear signal for small alpha. So this is only for your knowledge, just to know that in reality you use the four solar detectors, sun detectors in this configuration. In reality, however, we don't use analogic signal, but what we use is now digital sensors. So the concept is similar to this one. But instead of have 4 independent sun detectors, you have this reticle slit pattern. So it means that you have different columns of bits that provide you information regarding the inclination of the sun with respect of a specific plane. So for this one, for example, you need at least 2 of them, because you need to measure phi with respect to the sun sensor head. The main advantage of this configuration is that it is designed by using a gray code. The advantage of a gray code means that you have from each column a binary signal. So basically you have that the gray code as the output. So gray code means that, for example, you have first the 14. So basically, the angle is changing by a certain quantity. So you're starting from a signal that is 1, 0, 0, 1. If basically this angle is changing for just 1 decimal, the code will change by changing only 1 digit. So basically the second one will be, if you look at the in the book, you can see what I mean, just in-depth explanation of the gray code. So it means that, for example, if you have that at 14 decimal, the code, so basically the angle here is fixed. You have that your gray code bits give you this information of in bits. So basically discretize what it is given by the current in the analogic domain. So for each single measurement of phi, you have a certain response in binary code. The advantage of a gray code, if there is a change in the decimals, so for example from 14 to 15, you only change 1 digit. So the gray code means that every time that there is a change in the phi angle, 1 decimal of the phi angle, we only change 1 binary one binary code, one binary bit. So basically, what you are going to have is that this code enables a better discretization of your signal, and this configuration of the sun sensor give you the best accuracy for sun sensors of about 0.015 degrees, using larger field of views of about 70 degrees by 70 degrees. So if you want to have further information about the gray code and binary code, we can discuss that offline. But the only purpose to show you that particular configuration is to let you know that in reality, we don't have an analogic instrument, but we have a digital sensor that gives you a response in a binary code. And the one that is used is the gray code, because has a low variability of the digits coming from a variation of phi. So if phi changes, you are going to have a small variation of digits. The other code that you can use, for example, is the binary code. And for the same variation in the decimals of phi, for example, you will have, so if you do the same in the binary code, so the binary code means that if you have a change from the 14 to 15 digit of decimal of phi, so from 14 to 15, you have that 14 in the binary code is expressed in 0, 1, 1, 1, 0. The next one will be also 0, 1, 1, 1, 1. The problem is that when you go to the 16, the binary code switches from to this one to 0, 1, 0, 0, 1, 0, 0. For the gray code, this one will always be a switch in one digit. So you will have 1, 1, 0, 0. Why this is important? Because when you are in space, the change in the digits is very important to enable a best accuracy. If you have a change of 4 digits for a change in the 1 decimal of phi, that corresponds to basically a variation of 4 numbers. They could be affected by error sources because, for example, in space you're affected by radiation and other problems in the electronics, and that it is detrimental for your accurate determination. So that's the reason why the gray code is used, because it provides less variability in the expression of the decimals of phi, and it is very useful for space. I mean, this is only an additional explanation, a very brief explanation of the digital sensor for these sun sensors. But if you want to have additional explanation, you can ask me, or also read briefly the paragraph in the book that give you an overview on these 2 codes, the binary code and the gray code. So basically, every single columns give you a digit, and the basically the configuration of these columns, so how these digits changes because of the orientation of your sun rays, give you the precision of phi. So with that one, we conclude we can have can you still hear me? Yes, okay. No, I was trying to load the other presentation. So in the meantime, if you have any questions, let me know. but I would like to start with the second module of the course. So addressing some of your issues regarding the slides, this part of the course will have a completely different I mean, the order of the slides is completely different to what you have on the original one. I also filter out many slides that probably are not really helpful for a better understanding. So I try to focus, to concentrate to the main concept that we're going to see in the next part. So as I said, if you have any questions regarding the active determination, or also the hardware that we have seen, let's try to have an extra hour this week and next week. But now what we need to do is to address the other important question that this module try to answer. So far we were able to determine what are the sensors that we need for active determination and the algorithm that we can use to reconstruct the orientation of the spacecraft with respect to the inertial reference frame, or, for example, the orbital reference frame. So we faced that problem. Of course, that required the knowledge of quaternions, so we went to a demonstration of algorithm like the Quest algorithm that requested this kind of formulation. In this part of the module that we need to address the control theory of the spacecraft, the basic concept that has to be known in advance are the Euler equations and the Laplace transform. So if you have any concern about these two important preliminary concepts, let me know in advance. But I assume that you are able to I mean, you already treated the dynamical equation of the attitude from previous courses. Anyway, I will provide you a quick look back to the equations that was already treated in other courses. For the Laplace transform, I also provided some view graph that give you the main properties of this transform. That will be very important when we are going to look at the stability of the spacecraft. So why I'm saying that? Because it is important that you know that those preliminary concepts has to be well known. So I invite you, if you have slides from other courses, especially for the attitude dynamical equations, to give a brief look back. Although, as I said, I report in this updated version of the slides. So the main problem here is that we now are able to determine the altitude of the spacecraft by using the sensors that are on board. For example, star trackers and gyroscopes using the Quest algorithm and the extended Kalman filter. But the main goal of altitude determination and control is indeed to know the spacecraft orientation, but especially to let the spacecraft reach a specific orientation, a specific task. In space, you can find multiple examples of that. All spacecraft need to control its altitude. If you have a telecommunication system, you want to orient your antennas towards the Earth to establish communication to Earth. If you have a spacecraft with cameras or other instruments like laser altimeter, you will need to know your altitude precisely to maintain an ideal pointing to the Earth, so facing the optical bench frame towards the Earth, in order to determine the orientation of in order to control that your spacecraft is exactly pointing where you want. In order to approach that problem, we need to distinguish between two different approaches. As you know, in general, you have passive control and active control. Passive control means that you use a specific external force in order to maintain the orientation that you want. The active control is, on the other side, based on the use of auxiliary actuators. So you need to use those actuators in order to determine, in order to control the orientation of the spacecraft every single time. So of course, the first solution is has the advantage to not use any additional actuator. So is of course convenient in terms of mass and power, but it is very limited in terms of precision. And especially now that you need very demanding requirements of the attitude control of spacecraft, this approach is not indeed the main approach used. We are going to focus especially indeed in the active control, but to have a clear understanding of what we are going to do, in order to determine the how to control a spacecraft, first of all, we need to determine the stability of the system. So what we are going to do is to introduce the dynamical equation of the attitude of the spacecraft. So because the difference with respect to the previous module, in which our goal was to determine the attitude, the orientation of the spacecraft, our goal now is to control. So we have to induce torques to change the orientation of the spacecraft itself. That's the reason why active control are, yes, more complex, more expensive, but represents the main actuators, so the main strategy, because give you the possibility to direct, control the spacecraft and to point one axis towards the desired orientation. So here we need to introduce the dynamical equations. And before introduce the dynamical equations, we need to refresh the a bit the reference frame that we have seen even in the previous part of the course. So what we are going to see is that in this case, we're not going to write, for example, the dynamical equations in terms of quaternions. What we are going to use is an approximation in which we are going to assume that our goal is to control the spacecraft body frame to be close to the orbital frame of the orbital frame. So what we need to do, our goal, is to keep, for example, a spacecraft nadir pointed. So have, as we're going to see, that our spacecraft reference frame is going to coincide with the orbital reference frame. So the main goal of this attitude control system is to determine and accurately reconstruct the spatial orientation of the spacecraft. That was accomplished from the previous module of the course. Now we need to use those information to reorient the spacecraft to the desired orientation that we want. So the fundamental components that we have seen so far are only the attitude sensors. And we also introduced the software that you need to process those measurements. What we need to introduce for the remaining part of the hardware that we need to introduce are indeed the actuators. what we're going to see in particular are the thrusters and the reaction wheels. The flow of this part of this course, as I said, we're going to start from the stability of the system. So basically, by assuming only passive control, and we are going to include one actuator at a time in order to see how, from a generic spacecraft, we are able to control exactly the spacecraft as we want. So the passive control represents the basic concept. So we have a system, and we have to define a system in a way that is stable. So here you have the picture of the orbital reference frame. You have to keep in your mind that so the pitch axis is the y, roll is x, and the z is the yaw axis. You have to be careful that since z is neither pointing, so it's towards the Earth's center, the y direction is opposite to the angular velocity of the spacecraft if this is moving in, so this is omega 0. This is the angular velocity of the spacecraft, so the orbital angular velocity. So omega 0 here is the angular velocity of the, so basically is your, coincident to the angular momentum of the spacecraft orbits. So if we assume that the spacecraft is orbiting in a circular orbit, omega 0 is opposite to y, okay? This information will be important later. The other reference frame that we have to take into account is the body reference frame, that is related only to the design of the spacecraft. So you have exactly the information of the center of mass of the spacecraft, and you choose the body frame in order to have that all the reference frame corresponds to the principal axis of the body. Why we need to have that? Because we need to know what are the moment of inertia of the spacecraft. So in the body reference frame is fundamental because will definitely provide an easier representation of the dynamical equations. Our goal, as I said in this module, is to have that this reference frame will be basically will coincide to the reference frame of the orbital reference frame. So here you have the spacecraft. So you have to assume that the reference frame of the spacecraft is indeed aligned to the orbital reference frame. So the x here should be basically coincide to xbf. Same for y and same for zeta. Okay, so this is our main goal. The reason why that you have to keep in mind is that the reference frame that we want to use in our dynamical equation is the body frame. Why? Well, so let's now give a quick look back to the dynamical equations of the attitude. If you want to determine the dynamical equations in an inertial reference frame, you know that the time variation of, so the the time temporal variation of the angular momentum is equal to the external torques. So for an inertial reference frame, so EF, for example, if you know the angular momentum in the inertia reference frame, so the angular variation is exactly equal to the disturbance, or actually the torque expressed in the inertial reference frame. However, as I said, this not represent a convenient form, because if you write out, so this is inertial reference frame, if you compare EF, IF, so if you want to explicit H, as I said, is depends on the tensor of inertia and the angular velocity. Okay, so if you try to do the time derivative of something that varies over time, because in the inertia reference frame the tensor of inertia changes over time, the inertia reference frame is not convenient, so we are not going to do that. What we are going to do, we are going to write the dynamical equations expressed in the body frame. When you don't have an inertial reference frame, if you want to compute the dynamical equations, you have to express the angular momentum, so the dot product, so the temporal variation, the time derivative of H, plus the angular rate, so the spin rate of the body frame with respect to the inertial reference frame. So how the body frame is spinning with respect to the inertial reference frame. So this represents indeed the expression that you have to use when you have something expressed in the body frame. And here we are assuming that in the satellites there are not external actuators. So the moment, the angular momentum is only given by the H satellite. We're going to see, for example, that when we are going to treat the reaction wheels, the total angular momentum of the system will be the angular momentum of the satellite plus the angular momentum of the wheels. Here we are considering only basically our bus, so the box of the spacecraft that is orbiting the Earth with a circular orbit. What we want to do indeed is to explicit this dynamical equation in this form. So those are the Euler equations, because if you write in this way, you know that the tensor of inertia will be a diagonal matrix with the diagonal matrix equal to the principal moment of inertia of the spacecraft. So you can explicit this form in these three equations. And since our goal is to have that X body frame, Y and zeta will be close to the orbital reference frame, our goal is to express these equations with respect to the roll, pitch, and yaw angles. The main point that we have to emphasize here is that the torque that changes the angular momentum of the spacecraft over time depends on the control. Those are the control torques that for the first part we are assuming to be zero, and the disturbances. So that could be, for example, the drag, but as, for example, so there will be the everything that can perturb the spacecraft orientation. So for the beginning, we are assuming that both are zero, basically. We're assuming that the spacecraft is orbiting around the Earth without any perturbation and control. Okay, so our main goal here is that we found out that this is a three-second order nonlinear equations. What we need to do is to try to find a linearized form of the equations. That's the reason why what we want to do here is to determine the dynamical equations with respect to small angles, so to small variations of the body frame with respect to the orbital reference frame. There are any questions so far, or I can go ahead? So if there are not any questions, the main purpose of that, so I'm pretty sure that you already seen in other courses, but let me recap how to go from the nonlinear equations to the linear equations with a circular orbit. So what you can see here is that the omega that you have here is the omega of the body frame with respect to the inertial reference frame. But all these vectors are expressed in the body frame. Let me show you what I mean. So this is the Earth, and this is the inertial reference frame. So your spacecraft is moving along this circular orbit, and you have your xb, yb, and zeta b, your body frame. The orbital reference frame as defined as we have seen before. So zeta 0 corresponds to the yaw axis, zeta 0 the roll axis, and y0 the pitch axis. So our goal is to have that xb, yb, and zeta b will be coincident to x0, y0, and zeta 0. So every single vector will be expressed with respect to the body frame. What it means that even if we are trying to determine omega, so the angular velocity of the body frame with respect to the inertial reference frame, that corresponds to a vector that can be expressed in the body frame. So let's start from the first vector that we have to take into account. So the first vector is the angular velocity between the body frame and the orbital reference frame. So this is omega br. Every single vector, as I said, is in the body frame. The second vector is the omega of the reference frame, so the orbital reference frame with respect to the inertial reference frame. In the next slide, all those vectors are explicitly stated. The third vector is a little bit more complicated because it is the angular velocity of the orbital reference frame with respect to the inertial reference frame, but in the body frame coordinates. Okay, so between these two, so these two vectors are exactly the same vector. The only difference is that this vector here, let me write down, so omega Ri is basically the attitude matrix omega Rib. Oh, actually is the opposite. So this is Rib, Ri. So basically you need to rotate this vector from the inertial reference frame to the body frame. But our final goal is to find omega bi. Omega bi is indeed what is written here. So it's the body frame, the angular velocity of the body frame with respect to the inertial reference frame. Okay, so let's start with a simple one. So we know that the angular velocity of the body frame with respect to the orbital reference frame is expressed with the components P, Q, R. That will be clearer just the next slide. The other component, it is omega Rib. So the reference frame with respect to the inertial reference frame, but in the body frame. So what it means that these are the components of the reference frame with respect to inertial reference frame expressed in the triad xp, yb, and zeta b. So what we need to know is omega bi, that is the sum of these two vectors that can be summed because are expressed exactly in the same reference frame that is the body frame. To explicitly write what I mean here is basically that we know that omega, so the orbital reference frame with respect to the inertial reference frame has only one component that is opposite to y, that is omega 0. This is the mean motion of the spacecraft, okay? Since we are considering a circular orbit. This one, however, is expressed in the inertial reference frame. So we need to transform this one from the inertial reference frame to the body frame. So here we start to assume that the body frame and the orbital reference frame are very close by, okay? And so what we are doing here, we are assuming that the two reference frame can be, so the rotation between the two can be done by doing a rotation matrix that is only dependent from the angles. So this is the rotation matrix for small angles. So if you multiply this matrix to this vector here, what you get is indeed the orbital reference frame with respect to the inertial reference frame expressed in the body frame. So we have the angular velocity between two frames expressed in a third reference frame that is the body frame, because our goal is to express everything in the body frame that are computed dynamical equations. So what you can see here is that the omega of the body frame with respect to the inertial reference frame is equal to the sum of this vector and the second vector that is given by the product of that particular angular velocity to the rotation matrix that is defined here. Since we are assuming small angles, omega BR PQR corresponds to small variation of the roll, pitch, and yaw axis. So we can directly find that the omega of the body frame with respect to the inertial reference frame for small angles can be easily approximated to the these small angles approximation. So we can substitute, and tomorrow you're going to see better, to the vector omega of the body inertial reference frame with this expression of phi dot, theta dot, and psi dot, and also the angles yaw and roll. So if we substitute, first of all, we can also do the derivative of omega in order to determine also omega dot as a function of phi and psi and theta. So our goal basically is to arrive from the dynamical equation expressed in the general form with the Euler equations by using the small angle approximation in roll, pitch, and yaw axis that give you this final configuration here. So tomorrow we are going to deal with this linearization because it is fundamental to determine the stability of the system. So from tomorrow we are going to indeed study the stability of the system without any actuators, and we also see if we have a disturbance that perturbs its state. That will be important in a starting point, because from that one we're going to see how to develop actuators to stabilize the spacecraft attitude of the spacecraft. So the spacecraft attitude over time. So as I said, those slides are completely different. So I will upload on the system. If you find anything that is not clear, let me know by email. And if you have any question, let me know.